All right, we're going to discuss period frequency and angular frequency. Let's bring up the PowerPoint. And here we go. Let's move this off to the side. The period t of the shadow in this figure from before, which represents the time required for one complete trip back and forth, is also the time it takes the ball to make one complete circular trip on the turntable. Because the ball moves through the distance equal to the circumference of the circle, 2 pi a, in the time t, the speed v0 of the ball around the circular path is shown here, with the period t defined as shown. T equals 2 pi a divided by v0. Imagine that the ball moves from P to Q. That's from like the 3 o'clock position to the 12 o'clock position. Imagine the ball moves from P to Q a quarter of a revolution. The motion of the shadow is equivalent to the horizontal motion of an object on the end of a spring. So the radius A of the circular motion is the same as the amplitude A of the simple harmonic motion of the shadow. Basically, the amplitude. A is the amplitude. During the quarter of a cycle, the shadow moves from point A, where the energy of our ball spring system is solely elastic potential energy, to a point where the energy is solely kinetic energy. We can apply conservation of energy. We can apply conservation of energy. Let's solve for A over V0. Now, substitute to get an expression for the period t. And there you have it. T equals 2 pi square root of m over k. We see that the period is the time required for an object of mass m attached to a spring with spring constant k to complete one cycle of its motion. The square root of the mass is in the numerator. So a large mass will mean a large period, which agrees with our intuition. The square root of the spring constant k is in the denominator, so a large spring constant will yield a small period. It's also interesting that the period doesn't depend on the amplitude A. A is not in the equation for period. Okay. The inverse of the period is the frequency of the motion. So the frequency of the periodic motion of a mass on a spring is shown here. The units of frequency are cycles per second, 1 over seconds, or hertz. Here is an expression for the angular frequency, omega. 2 pi f equals square root of k over m. The frequency and angular frequency are actually closely related concepts. The unit of frequency is cycles per second, where a cycle may be thought of as a unit of angular measure corresponding to 2 pi radians or 360 degrees. When we look at it this way, angular frequency is just a unit conversion of frequency. Radian measure is used for angles mainly because it provides a convenient and natural link between linear and angular quantities. So in our ideal mass spring system, the period is proportional to the square root of the object's mass. Experiments showed that a graph of t squared versus m doesn't pass through the origin. This is because the spring itself has a mass. The coils of the spring oscillate just like this object, except the amplitudes are smaller for all coils but the last one. For a cylindrical spring, the effective additional mass of a light spring is 1/3 the mass of the spring. The square of the period is proportional to the total oscillating mass, so a graph of t squared versus total mass, which includes the mass hung on the spring, plus the effective oscillating mass of the spring, would pass through the origin. Okay, the next we're going to talk about position, velocity, and acceleration.